So thank you for joining us in this in-depth session where we will discuss the next generation component testing. So as you know, when you're testing a photonic integrated circuit, a PIC, you need to find the component on the wafer, align the output, input, probe, or fiber. And once it is done, you could measure the characteristic of the components. So joining me today for this technical interactive discussion, we have Simon Waite, senior sales engineer with Elliott Scientific since 1998. So Simon is responsible for the component group, offering product to the research community for over 25 different suppliers, including Elliott owns alignment and micro positioning products. Simon will demonstrate, in fact, the micro positioning system, including heat mapping, alignment tracking, output 3D profile. Very, very hands-on, so it's a very interactive session. Welcome, Simon.
Thanks for joining us today. Glad you could all join us here. So I'm just going to share my screen here and begin with the little talk.
Just before you jump in, I'm going to introduce Francois as well.
Sure. Yeah, no problem.
Yeah. So also with us is Francois Cooney, product line manager at Expo, and Francois is responsible for the optical component characterization equipment. So ranging from optical spectrum analyzer to tunable laser sources and component testing platforms. And Francois will demonstrate the insertion loss and PDL testing using the CTP10. So welcome, Francois. So please don't hesitate to ask any questions to Simon or Francois in the chat on the team. It's a very interactive session, so you can ask questions and you can raise your hand as well in the teams. And we will try to take as many questions as possible during the event. Finally, bear in mind that this session is 30 minutes and we give it twice. So we're going to give it again in about 20 minutes, 25, 27 minutes. In that way, you will also be able to attend another sessions or this session if you arrive in midterm. And please refer to the Expo event platform for information. This session is recorded as well and will be available on the Expo platform for the months to come. So without further ado, I give you the mic.
That's great. Thanks, Gwyn. So I'll just share my screen. If there's any issues with the sound, let me know. But hopefully we should all be okay here. So I can introduce you with a few slides.
We work closely with our principal partners like Expo, combining knowledge and expertise to provide bespoke solutions for each application. This often requires a combination of the specialty test equipment from the Expo range and the mechanical alignment systems manufactured by Elliott Scientific. Our own positioning range, established over 30 years ago, developed its reputation in the years leading up to the first telecom boom and is a well-trusted and relied upon brand offering longevity, quality and performance. I'll just run through a couple of slides here to give a brief introduction before moving on to the demo. The starting point for any of our fibre alignment solutions would be our XYZ flexure stage. Compared to our other positioning systems like bearing and crossed rollers, for example, the flexure stage offers an ideal combination of precision, isolated axis motion, travel and stability. The stage can be fitted with adjusters to suit the alignment precision requirements, so for less demanding applications such as large core multimode fibres, we could start with standard manual adjusters offering 1 micron resolution. For more precise single mode and polarization maintaining launch applications, we would move to the high precision manual adjusters based on a patented mechanical lever system, which is the highest resolution mechanical adjuster in the Elliott Scientific range. We also offer piezo adjusters, which I will show working with our automated alignment system shortly. The typical alignment requirements for a fibre to device to fibre application are met by our waveguide alignment workstation shown here, incorporating an XYZ flexure stage on either side of the central tower. The central platform is fitted with a digital micrometer, allowing a precise linear step control, for example of a waveguide chip, so the end user can step between channels. Travel range options here are 25mm and 50mm, facilitating testing on larger chips or devices. The flexure stages are mounted on a rack and pinion slide both sides, with rapid coarse travel range 60mm. This allows the user to disengage the launch coupling platforms, load a different fibre assembly, and then redeploy to the device under test quickly and without worry of crunching the fibre tip into the device under test. For automation, we move to our piezo adjusters and have two options here, a 25 micron travel and a longer 100 micron travel adjuster. we have our own 3-axis piezo controller, and for the automated solution, would combine this with our DALI instrument. The DALI takes either an optical signal directly from an optical fibre or an electrical signal direct from an external power meter, and then, depending on the requested function, outputs signal to the piezo controller. Some system features of the DALI 4 automatic alignment profiler version are profiler modes for output uniformity analysis, 3-axis precise piezo control, operation via software or manual controls, superior search and optimize routines and algorithm, store parameter sets for each alignment and export the data, full control over the scan parameters, USB interface, LabVIEW drivers included for integration and bespoke control, and a power meter display. This really highlights the synergy between Elliott and EXFO here, as the end user could use a T100S fibre coupled source, combine with the Elliott stage to launch into the device under test, or step through multi-channels in a waveguide, recouple to a fibre on the output side, and then send off to the OSA 20 or component tester platform. So now we'll move on to the demonstration of DALI. Firstly, showing here our flexure stages, adjuster options are fully upgradable and a wide range of accessories can be mounted on top, for simple fibre launch using bare fibre holder and an objective lens holder to a full 6-axis positioning, giving pitch and yaw and rotation control. Our automated system is shown here with the E1100 3-axis controller, DALI unit and stage fitted with piezo adjusters. The DALI here is configured to receive optical signal and process using a built-in photodetector, or we can select input signal directly via BNC from an external detector module. Output control is sent to Y and Z on the 3-axis controller, which then controls the voltage going to the piezo adjusters. In this setup, we are showing a simple fibre-to-fibre launch. On the moving platform, we are delivering the fibre-coupled source, and on the fixed part of the platform, we are then coupling the signal and sending this directly into the back of the DALI unit. This is DALI software interface, showing for this demo a single data acquisition board monitoring input and controlling 2 axes. Alignment signal is set to internal detector, as we are just feeding the coupled optical signal straight into the back of the DALI. To start the process, we select search mode, which effectively runs a raster scan over the full 0 to 150 voltage range on the piezos. So would cover a 25 micron or 100 micron square, depending what piezo adjusters are fitted. In this demo, we have a 100 micron piezo fitted and would make manual adjustment when required to center the signal. In the case of waveguide stepping, you might be using a digital micrometer to move 250 microns or 500 microns between each channel. Some manual adjustment is shown here, centering the signal in the middle of the scan area. Once track mode is engaged, the DALI performs a dither scan and monitors controls the piezos to achieve the highest signal. Dither amplitude voltage can be varied to a larger circular scan, or a tighter lock is achieved on a peak signal. While in track mode, the system compensates for any movement of the fibre position with respect to the device under test, or in this case, the other fibre. As a deliberate misalignment force is applied, simulating movement of parts, for example, during curing, the DALI will adjust alignment to maintain the highest signal level, and by changing voltages to the piezo. It corrects when the force is removed. And here we are observing the relative coupled signal, which is the blue bar along the bottom. And as we push on the stage, this drops off quickly, but rapidly returns as the DALI corrects. In hold mode, the voltage to each piezo is fixed, and this might be done during the latter stages of curing, for example. We can manually control the voltage via the graphical user interface, and as we do so, we can see the signal drop off as we move out of optimal alignment. We could re-engage track at this point to recenter if required. Now we move on to scan mode, where we can build a profile of the output from the device under test. To start, a quick scan is shown over the full travel range of the piezo, and with quite large voltage steps. For a more detailed output profile, the minimum maximum voltage boundary can be set and much smaller voltage steps between this range. At each step, the signal level is logged from either the external detector or the internal detector in the DALI. And in the case here, we're running a high resolution scan over a smaller area to generate the 3D profile. This may take a couple of minutes depending on the voltage boundary set and the incremental steps within that range. The 3D generated profile can be manipulated within the DALI software so that you can look for any observable structure on the output. This might then require further interrogation by limiting the voltage range further and taking even smaller steps for a higher resolution scan over that area. This data can be exported as a CSV file. For this demonstration, we are using FC connectorized fiber holders, a wide range of building blocks options for additional alignment functionality, along with a wide choice of accessories to accommodate different fiber terminations, bare fibers, fiber V-groove arrays, ribbon fiber, waveguide chips, and other photonics devices is available to take care of the mounting and alignment requirements for next generation component testing. A couple of slides here show some of these accessories. We also offer a ferrule holder for larger diameter packages, so alignment of pigtail collimators or focusers is possible. A range of vacuum mount accessories is available. Long reach connectorized and bare fiber holder options offer additional flexibility. Adjustable force grippers for fibers or small collimators and ferrules was developed and allows for delicate high precision manipulation of a tapered, lensed or bare fiber inside a hermetic butterfly package. For PM applications, we have high precision fiber rotators, and a dual motorized rotator can be configured for applications using photosensitive fiber and writing structures onto these fibers. This brings me to the end of my part of the talk, and I shall hand over to Francois now to cover the EXFO testing capabilities. Thank you.
So great, excellent, Simon. So you provide pretty much everything you need, manual, semi-automated, automated, to compose light into a device, it being a fiber device or otherwise. So now comes the part of the testing. And as you can see from the screen here, we provide the testing part on the optical side with a tunable laser and a CTP10, OSA20, which is the optical spectrum analyzer, or the CT440, which is a more compact component testing platform. And so today I will talk about the CTP10. And so the CTP10 is a component testing platform 10 because it has 10 slots. So it's a modular platform, always operates with the T100SHP laser, either 1, 2, or 3 lasers, depending on how much band or wavelength range you want to achieve. So with 3 lasers, you can achieve from scanning from 1240 nanometers to 1680 nanometers. So if you know your bands, that's OES, CL, and U band in the telecom. Because it's modular, you can have detector modules. So if you have up to 50 detectors, that's 50 output ports that you can test at any one time per mainframe. And that can be increased if you add one additional mainframe to about 100 detectors. The dynamic range of the measurement that we are going to see is roughly 70 dB. Actually, it's larger than 70 dB in one single scan. And this is achieved by a combination of electronics and the software algorithm behind that gives us a single scan full dynamic range. In terms of wavelengths, we have a 1 picometer sampling resolution and a plus or minus 5 picometer accuracy, and a lot of built-in analysis functions. So let's have a look at what it looks like in real life, and then we'll have a look at the software, the GUI, the graphical user interface, on how to operate it. So you can see the CTP10 on the top, the T100 SHP lasers that we'll use with it, and we have a screen. You can also connect up keyboard and mouse, but that's optional. I mean, you can fully automate the system, but if you want to have a look at what's coming out, you can connect that. Surely you need to connect the tunable laser to the platform. So this is done on the RS232 port of the tunable laser. And you switch them on at the back and switch them on at the front. So the system will take about a minute and a half, 2 minutes to start up. The CTP10 is actually a PC inside, so it takes a little while to warm up. So while it warms up, you can set up which module you want to use. In this case, for example, a module has been inserted. It's hot swappable, so it's automatically recognized by the software. And here you can see it was an IL, RL, OPM2, so insertion loss and return loss measurement module. Second module was inserted. It was a full band combiner module. So we didn't really talk about cleanliness, but this is very important for PDL measurement particularly. So we'll talk a little bit about PDL measurement in a few seconds. So now the principle of the CTP10, and I touched a little bit about that in the panel discussion, is that you tell the CTP10 what your setup is. So here, the idea is to reproduce the setup that you physically have onto the screen of the CTP10. Telling the CTP10, I'm using a DUT that had 4 outputs, and I've connected them to these ports, and I'm using this particular laser. And so you're pretty much all set here from a setup perspective. Now you want to test a particular wavelength range. So you set up the start and stop wavelength range of the scan, the spectral scan that you want to perform. You can also adjust the sampling rate, etc. And now we come to one particular aspect that I like about the CTP10 is that it's the referencing is integrated into the device. So the referencing means taking a measurement without the DUT. And later on, we'll add the DUT, and this insertion will give us the insertion loss. So we perform this scan without the DUT over all the relevant parameters that we'll use, the detectors that we'll use. And now we're ready to add the device in the test. In that case, it was a LAN WDM, so 1 common port and 4 outputs. And we just press scan to perform the test. So you can see at the top right corner the progress, 100%, 4 scans, 4 polarization to perform insertion loss and PDL calculations. And straight away, you also have analysis for each of these channels, each of these outputs in terms of PDL, center wavelengths, and so on. From the trace perspective, you can fully control the color aspect of the trace, make it visible or invisible so that you can see clearer one or the other. And if you don't want to measure PDL, but just transfer function, just insertion loss, you just 2 clicks, just disengage the PDL calculation, and here we are setting off a scan mode that is continuous mode. And here you can see the number of scans. So once again, at the top of your screen on the right, the progress and the number of scans being performed. It's much quicker. So for alignment purposes, in this case, it could be a good solution to use. So that's to give you a rough idea of what is possible with this CTP10. Obviously, I could go on about every single aspect of the GUI, particularly daisy chaining or laser sharing, the fact that you can save full configurations and load them back again a bit later on. But I will stop here and hand it back to you again, Gwen.
Well, thank you, Francois. Thank you, Simon, for the presentations. So we have some time for Q&A. So this is great. So if you do have any questions, we will take those questions. Don't be shy.
I have one question for maybe Francois and Simon about using the DALI system together with the CPT10. Is that possible?
Yes, yeah. Well, from our perspective, the DALI system, it looks like it's using a photodiode output to perform the alignment or to perform the measurement. And on the CTP10, and let me just go back once to the end of the presentation. Here at the bottom, we can see the analog output here. So you can select any of the outputs to be used as an analog output at the back of the instrument. At the back of the instrument, you have a BNC that will output the equivalent of what is received by the photodiode. And because the CTP10 is a very fast system, with averaging times down to 1 microsecond, then that I think is well suited for use for alignments such as the DALI system. I don't know, Simon, if you wanted to add on that.
Yeah, that's exactly. It's the DALI. You can select an external source, so the input for that is via BNC at the back of the DALI. So in your alignment process, you would just select external source, and then you could connect up, as you say, to the output there from the kit there.
Very good. Thank you, Simon, and thank you, Jeff, for the question.
I do have a question, in fact, for Simon about Python. So for the DALI, if you want to automate the setup, what do you offer for a Python program language?
So at the moment, the software interface, it's done via LabVIEW, but there are a number of additional features that we'd like to add to the software. So some customers have asked us for auto-focusing. At the moment, we're just doing the signal on the Y and the Z axis, but for actual analysis through the focal points is something that has been requested. So as we add those features, we are planning to write the new interface in Python because that will give us a little bit more flexibility, and end users will probably prefer that sort of interface now as opposed to LabVIEW. So that is something on the plan for us to develop that.
Okay. And Francois, by the way, for the CTP10, I think we have some examples as well in Python, if I'm not mistaken.
Yes, so with actually not just the CTP10, but every instrument that we ship, we provide an example in a few languages, programming languages, including Python and LabVIEW. Yes.
Perfect. Thank you. Any questions? This is the right time.
I think we had a question on the
chat.
On the chat. So what kind of a laser do you have in the sweat wavelength source? So this is yes, and actually it has been answered by Wei Fi. So thank you, Wei. It is a tunable laser Expo T100 SHP. So it has to be a continuously tunable laser. So meaning that as we sweep the wavelengths, we have a good enough control over the wavelengths so that we can read at the same time what the power is on the detectors. And from all this information, we can infer what the insertion loss spectrum is, or the PDL, or the return loss, depending on which module is being used.
And Francois, you mentioned daisy chaining. What's the kind of upper limit? I mean, can you test, say, 100 outputs on the...
Yes, yeah, so it's possible to use a daisy chaining, so basically having one extra mainframe CTP10 full of OPMs. This is the module with all the photodetectors. And so with this addition and basically linking them with a BNC cable and Ethernet, you can have, I think the limit is 104 detectors in the worst situation if you were using full band combiner and IL, PDL, OPM2. So these take up a little bit more slots on the device.
Okay. And following, in fact, the same question from Geoff. So if we wanted to test multiple inputs, multiple outputs with multiple wavelength ranges, this is also something possible, right?
Yes, yeah. Well, multiple outputs is possible in one single scan because we have so many outputs. Several inputs with the help of maybe external switches or matrix switches. It's also possible to test, from several inputs to several outputs at the same time. And in terms of wavelength range, and I touched a little bit about that in the panel discussion also, is the fact that you would need several lasers, but the CTP10 would combine them together and provide you with a simple solution that you don't have to switch to laser 1, switch to laser 2. Everything is taken care of by the CTP10.
Perfect, thanks. Any other questions from our attendees?
I see on the chat, Francois, a little bit more a question about the laser itself, the type of laser within a T100 SHP. Can you say any more about the external cavity design?
Well, it's an external cavity laser without any mod hop. And so, as I said, it's a continuously tunable laser. So the scan can be detected, or the wavelengths can be detected with a resolution of 1 picometer on the CTP10, simply because the linearity of the displacement of the wavelengths if you want, is so smooth. So it's not a DFB, it's not an ITLA, for example. It is an external cavity laser, but that provides the tunability required for the CTP10. The other advantage, if I may finish, this on the T100 SHP laser is also the very good extinction ratio of the laser. It has a very pure laser line, which means that particularly for passive components, makes it very, very good because you can really interrogate the device to the 70 or 80 dB of insertion loss that you need.
Well, thank you, Francois. That's all the time we had for this session.